Everyone. Today's lecture is going to be on penetrant testing as well as magnetic particle testing. Before we go into that, just a quick recap of the first four lectures. We had discussed film radiography, so I actually had found some actual films of the wedding cake samples that I had showed you with the multiple layers. So not sure if you've ever seen actual traditional film radiography before, but what happens is, this is the film here. If you actually put it up against the light, you can see the samples, but in general, what they'd have is a backlight that you put this on, like when you go to the doctors and if you broke a bone or something, they put the X-ray scan. Same type of thing, you put this up there and it shows the X-ray voltage, and it also has some identifying information. For film radiography, they do what's called a IQI, and that is a way they can calibrate the film. So they put specific materials of a known size, whether it's 5 millimeters or something like that. So you can take a look through these, but I wasn't sure if you had ever actually seen film radiography before. In general, you don't touch them with your hands, but you can go ahead because that was from my thesis. So my thesis has already been published. So if it gets messy, I'm not really worried about that. We had also discussed in the eddy current lecture yesterday the issue of liftoff as you go over the sample with the various probes. So what I did want to show was this is what is known as a duct segment, and this is part of an airplane component. So you have in the airplane engine, you have discs and blades, but you also have other components. So as you see here, it has complex geometry of various shapes, but if you look closely, you can actually see the indications, the cracks on the surface here, and you can actually see there is a bit of a taper as you go over the sample. So this is the issue of liftoff from when I showed you the video when the inspector's going over it with the probe. And what shows on the traditional eddy current is the Lissajous signals. That's the ones that kind of look like butterflies on the XY scan. That is a function that there is a bit of a saddle to the component. Just a quick overview chart on the various methods that we've gone over so far and their applicability for both two-dimensional and three-dimensional. Two-dimensional, they're cracks. 3 dimensions, they're voids or inclusions. So certain techniques, visual testing, you can really only get a surface view. So there is no opportunity to see an inclusion just by visual exam. As we discussed yesterday, the eddy current exam has capability for near surface inspection, but it drops off as 1 over the square root. So when we say near surface, we're only talking millimeters before you lose that resolution in the sample. The one that has the capability to do both surface and interior, you got the ultrasonic testing, and in some instances you can use computed tomography for surface flaws as well, but that essentially, rather than it being the entire 3D sample, you're only concerned with a couple of the 2D slices right at the surface. So basically, the point is there is no silver bullet when you're doing non-destructive testing, and if it's mission critical, so I don't know if you guys saw it, but I saw Elon Musk walking past my window this morning, so I guess he's giving a talk or he's here for a meeting. But if something's going out into space, then it's mission critical and it's worth performing multiple inspections and getting redundancy on. To follow up on the eddy current inspection, so we had discussed the calibration that needs to be done. It's specific to the material that you're inspecting. So if it's an aluminum alloy, if you look closely on this image, there are actually indicators on here for various types of flaws. So when you put the probe over these, this is how you self-calibrate the equipment to do the inspection. This was a commercially available 32-channel array. And one of the issues that you see is this is the difference with just a 32-channel array that does not collect data simultaneously. So there's 32 channels that collect 32 pieces of information, as opposed to the what's known as the meandering winding magnetometer, which it can have more than 32 channels, but it's the way in which the data is collected and is the way in which the data is normalized. So you can see the difference between the two. There are some ways that you can use an off-the-shelf technique to improve resolution. One of them is known as multiplexing. So if we're talking ultrasonics, it's the way in which the ultrasonic sound beams are actually timed. They time the sequencing of how they send the various channels through the sample. That's the sectorial scans, and those are also the C scans. But you can see when we talk about confidence levels and resolution that if it comes down to an inspector who's qualified having to say if it's a part that needs to be removed from service or in service, you would probably rather have something here than something up here to be able to discriminate sizes of flaws as well as features of the flaws. With respect to eddy current testing, there are artifacts in the imaging that can lead to false positives. So when you see here these edge effects has something to do with the flat bottom hole, the signature of the flaw. So as the channel probe goes over that sample, what happens is you have multiple channels at different times, and these little blue areas, those aren't true locations of flaws. That is a product of the multiple channels going over the sample. So you can get what's known as ghost artifacts or just artifacts in the imaging. You see striping artifact down here. That is if you do not go over the sample with a steady hand, and at some point some of the channels have a liftoff, whereas others do not. You'll get the striping artifact because it's not going over with the same force over the sample. So there's ways that they can actually design in, with robotics encoders. So if you build in an encoder to the system, you can know exactly where along this XY axis you are at any point in time. And then they can also build in essentially like some type of robotic claw or something that puts a pre-stress onto the sample. So it's a uniform pre-stress so that you don't get these types of striping artifacts. Because if you're going over just with the hand, you will get these in imaging, and it's basically something that you have to, it's from experience only that you would have to know that this isn't really a heat affected zone. So if this was a sample where there could be residual stresses or issues from the metallurgical processing, you can get a false positive by not knowing the difference where heat affected zone versus if you didn't have the sample held down properly at some point are. So that's what these arrows are pointing to, certain artifacts in the image that are not true indications. The true indications are the reddish colored circles. And what you can do is, by depending on how you set the range on the bottom here, if you can set it tighter or wider, it affects the C-scan output for the color image. One of the other things I wanted to discuss, whether you guys are undergraduates or graduate students, is that I think it's an opportunity that, and for the people watching on video as well, as a student, you can actually join professional societies at a very cheap yearly cost. And it's something that sometimes students who aren't material science students don't know. But for non-destructive testing in the US, the organization is American Society of Non-Destructive Testing. And you can actually sign up as a student for only about $15 a year. And then you can get access to the journal articles they have an entire digital library. So if you use 1 or 2 journal articles in your research, it more than pays for itself. And the other thing that is valuable with it is that you can sign up for fellowships. So for ASNT, they have 5 fellowships up to $20,000 a year. So if your research is related some way, or if you want to make it related in some way, there are very few people actually do graduate research in NDT. So it's a good way for funding purposes if you apply. So when I was a grad student, it wasn't $20,000, but I did get to go to a conference for free. So there is some value in these things. Some of the other societies related to materials are TMS, which is the Materials Society, ASM, which is American Society of Materials, and NACE, which is related to corrosion engineering. So for long-term operation, they call it asset integrity is like the buzzword they use in the oil gas industry. So if you've seen petrochemical engineering, it's really hot right now with fracking and different types of industry. If you even consider thinking that that might be an industry you want to go into professionally, then I would consider joining NACE as a student member, because they have same thing. They have a online database, and you have access to a lot of information for oil and gas coming out of the various areas of the U.S. where we refine those things. So for today, we're going to discuss liquid penetrant testing. So in the industry, it's known as PT. It's also, you can either see it seen as LPI, liquid penetrant inspection, or FPI, fluorescent penetrant inspection. It's one of the, other than visual inspection, because it's a low-cost way to inspect something, unless it's mission critical, cost really will be the driver on what techniques they use in the industry. So if you drive over Longfellow Bridge, at some point they are going to be doing magnetic particle testing or penetrant testing on the anchor bolts and on other connections, joined connections or otherwise. So these are things most people don't consider, but it's good to know. So fluorescent dyes render indications of discontinuities. The thing that is important to distinguish penetrant testing from other techniques is that it has to be something that is a surface cracking discontinuity. So if it was subsurface, I had shown the X-ray in the X-ray lecture that the blisters, and as we went through the thickness, you could see that was sulfidation of the blisters internal. This technique would not detect that. You would actually be able to put that part back in service. It would be a missed opportunity to indicate it, because they were not surface breaking flaws. So the difference, that's the difference when you want to use either an ultrasonic or a technique that has more depth of penetration into the sample. And then you use a UV light to basically I'll show you in some of the photos later, but under the UV light, whether it's fatigue crack or whether it's some type of branching crack, which would be indicative of stress corrosion cracking, you can actually see the crack profile better under the UV light than just visually. The advantages are that for complex shaped parts, you don't have to worry about the ultrasonic scattering of the acoustics. So if you put the developer or something on the sample, it relies on capillary action, and you can work around the geometry. And the main thing is that its cost is the main driver for most of these techniques. Compared to other techniques, it's a trade-off with respect to time. So sample prep, surface prep to get the surface to a proper condition is approximately 30 minutes to perform this inspection, whereas the eddy current's a matter of seconds. The other issue is that the variables, whether it is of the equipment itself or of the sample, it is sensitive to those inspection variables. So it leads itself to false positives more than other techniques. So as I had said in earlier lectures, there is a lost cost, or there's an opportunity cost. If you pull a part out of service that should remain in service, that can cost the owner operator as much as if you left a piece in service and it failed on you. So it's like a 2x2 matrix. The missed indication versus the false positive, and sometimes the false positive indication ends up costing the company more. And finally, it is reliant on the inspector's skill. So it comes down to the person who's performing the inspection's eyes, and it is more a subjective issue with respect to who's looking at it. So there's actually been published papers and research studies where they show the scatter. They take people who all are qualified as a level 2 or level 3. They all give them the same component with the same flaw, and they ask them to size the flaw. And there's quite a bit of scatter, even in people who are qualified to sign off on these things. So the variability from inspector to inspector is it's just another issue that relates to the confidence level when you're doing the statistics. A brief history of the penetrant testing. In the early 1900s in the railroad industry, it was known as the oil and whiting method. And the oil was actually usually a kerosene. And they chose kerosene because at its most simplest, this is a technique based on capillary action. So if you have some type of liquid that is hydrophobic to the surface, it will not perform as well as kerosene, because kerosene actually wets very well, better than just water. So they were used kerosene, and the whiting is essentially chalk. Not chalk like this, but they could use a powdered chalk over it. So that was used early 1900s in the railroad industry. What they would have to do is, it was very much reliant on the surface prep. So if you travel on railroads often, you will see that there are what's known as flat spots in the rail, where the wheels and the rail contact each other from friction, or sometimes if there's leaves or other things on the rail itself, it will cause flat spots in the rail. And the preparation on the rail head is important to the outcome of the inspection. Following up about 40 years later is when they started using the fluorescent dyes. So there's two different types. You can either have a fluorescent or visible dye. The fluorescent is where you use the black light, but you can also use a dye without a black light, and that's what's known as the visible dye. And it's typically like a reddish color. It appears as a reddish color after you give it the time to sit and develop. So one of the, some of the variables on this is temperature and soak time. So after you've prepped the surface, put the kerosene or other wetting agent on, you need to let it sit a minimum, typically 20 minutes, so that the capillary action will suck the moisture in if there is a crack surface or near surface. The variables other than surface prep and condition related to the component under inspection is the depth, aspect ratio, and length. So this is one of the catch-22s in the NDE industry. When they develop samples, test samples or calibration samples, they either typically use those flat bottom holes or side drilled holes. And the profile of those, so if you have a flat bottom hole, all right, you just think of it basically as like a square hat like that. In real life, the crack will take some type of tortuous path, so the aspect ratio at the surface to the bottom, this is when I'm talking about aspect ratio. In real life, the flaws aren't flat like this. They have various orientations. And you can if you deal with NDE as much as me, I read a lot of cut sheets or vendor manuals on what they claim they can detect. You have to be cognizant that oftentimes they're basing that detection capability on something that is not realistic in operating conditions for actual components. So if it says they can see 300 microns or something of that sort, you have to realize that you probably have to add a knockdown factor or something like that, and the actual flaw that you'd be able to detect in the field could be order of magnitude larger. So don't believe everything you read in the vendor manuals, because they're trying to sell you a product, right? But you have to realize that what are they basing their flaw thresholds on? And it relates to how deep the flaw is, the aspect ratio, length, and in the real world, they don't look like this, or they're not side drilled holes. They have various orientations to them. Cleanliness and surface prep are important for penetrant testing. If you don't prepare the surface properly, you won't wet, regardless of if you use kerosene or some other component, if there is oil or grease or debris. So if it's a sample where there could be corrosion, you will not, if you let it sit for an hour, the capillary action won't suck it into the flaw. You have to actually prep the sample properly. So that does involve some type of grinding sometimes, and if you're not allowed to grind the sample down to get a lustrous surface, then you have to start looking at other techniques. That's when you decide if you use an eddy current or ultrasonic technique instead. So the penetrants, it has a range. It ranges from level 1/2, which would be an ultra low sensitivity, to an ultra high sensitivity. So they actually have taken it into account. When you can go buy a consumable, it will tell you if it's for an industry where you need high sensitivity, you would go towards the ultra high level. So they actually, and that deals with how fine the emulsion or dispersion of the particle that they're using as the wetting agent is. All right, so in general, this is just published data, but as I said before, you need to take into account that this is published data based on not realistic flaws. So in general, the sensitivity of the technique is 5 microns wide by 10 microns deep for type 1, which is fluorescent penetrant inspection. So that number is based on flat samples. It's just based on plate, putting flaws in a plate. If you are not working with a sample that has that geometry, then you have to realize that the value will be larger than this. And the other thing to note, that your probability of detection is not going to be that 90%, and it's not going to be at that 95% confidence level. So if you are allowed to have a lower, in some industries, it's just a go, no go, all right? So they either see something or they don't. But in aerospace industry, they really do try to design towards a confidence and reliability level. There's 4 basic methods of penetrant testing. You have water washable, all right? You have other methods that deal with emulsified materials. So when you're mixing 2 different liquids together, if it's going to be miscible or immiscible, that is methods that you can actually purchase. And what you see is it's basically like an aerosol spray can. So the other thing to note is at the site, if you're out working in a field site or if you're working in a factory, sometimes there will be issues with actually using aerosol in certain factories if it needs to be temperature or humidity controlled for certain high value structural components. If you're out on a bridge decking or if you're out performing something on the green line or something like that, yeah, they they can go out and use the aerosol can out in the atmosphere. So the location where the part's manufactured versus if it's out in the field already in service sometimes limits what you can use. Flashpoint, the other thing is, since this is flammable material, that you have to look at the MSDS sheets, all right? So material safety data sheet. And in general, the flashpoint, which is the point where it can ignite itself, they want to be over 200 degrees Fahrenheit. So if you have something and it needs to go into a annealing furnace or have some drying operation, you often will be over that flashpoint. So just a schematic, since I mentioned it's based on the wetting and capillary action. Have you guys dealt with Young's equation before in kinetics or any of your classes? So one of the things that is also important to note, if there is a chance that you can actually get residual gas at the base of the indication. So one of the things sometimes you'll see is they'll tap the area that they're inspecting with a mallet or something like that, just to try to remove any potential gas bubbles or things like that. So you can actually determine if there is a flaw or not. This are the terms in the equation on the previous slide. So the cosine theta is your contact angle. You have a solid phase, liquid phase, and gas phase. So if you're in a factory, sometimes you're building something, fabricating it in an inert environment. So you need to take that into account. It affects the values for the gas phase, whether you're doing something under vacuum or not. And then this is an equation that will tell you the depth that the liquid will penetrate into the sample just via capillary action alone. And in industry, if you go travel to factories where they're designing aerospace components or other rail, if you go into steel mills, things like that, you will often see areas, this is where they would do the penetrant testing, and they have their developer area. And you'll see when you see the MSDS, you also will see this, whether it'll tell you how the hazard levels for the components you're using. So what's happening here is these are aerospace components, and they put the fluorescent on it and they just let it drip off. So this is a bath underneath here. They reuse the material that drips in that bath, but they can only reuse it a certain amount of times. So this, in industry, they have a quality assurance, quality control program, and there's all procedures and protocols that dictate how many times they can reuse the penetrants and things like that. This isn't particularly relevant for research, but in industry, it's important to note that there are standards and codes that tell you exactly how to perform the inspection. ASTM is American Society of Testing and Materials, and they have standards related specifically for liquid penetrant and these other techniques that we've discussed. And not only specific to the technique, but they have sometimes specific standards for processing. So if you were doing something by TIG welding or MIG welding, there could also be a specific ASTM for doing penetrant testing of those types of components. So how you assemble the component, how it's processed metallurgically, you need to know the correct standard that you are going to be basing the inspection on. In addition to ASTM standards, aerospace material standards, that's specific to the aerospace environment. ASME boiler and pressure vessel, so that is for pressurized tanks, that if you have ammonia tanks or other types of tanks that are under pressure, it's important because if somebody has to go in and do confined space inside the tank, you have to know, the proper standards, and there are limitations on on how you can actually do the inspections for pressure vessels. And then finally, the U.S. government, Department of Defense, issues mill standard codes. So Professor Eager actually has an entirely separate module on codes and standards. And if you're interested, then there's, I think it's a 6-lecture module on that. But under the fluorescent light, this would be just off the Magnaflux website, which is one of the commercial vendors that sells all these consumables. This would be something, what you'd see on various samples under the black light or UV light. For magnetic particle testing, it's not rocket science, but you need to realize that magnetic particle testing, since it involves magnetic particles, it can only be used on ferromagnetic materials. So you can't use this for if it's just strictly high density polyethylene. They're in transmission and distribution gas lines, they are moving from using cast iron and ductile iron pipe to high density polyethylene. All right, one of the issues is that it resists corrosion better, but the other issue is you have to maintain these things over, oftentimes they're in the ground 40, 60, 80 years. And you have to know that you can't use a magnetic particle technique on a polymer. You can't use it on a glass or ceramic. So it has to be ferromagnetic material, and there has to be a surface crack. So what's going on here is he's already put the ferrous particles. You prep the surface and you put the powder on the area, and what will happen is, depending on if you use a magnetic yoke, which you can see, or if this entire ring is the magnetic they can magnetize it externally, or they can use yokes or rings or other ways to magnetize the sample. But what will happen is, if there is an indication, the magnetic iron particles that you pour on there will align themselves, and you can actually get an idea on how large the crack is. One of the case studies that's discussed a lot is the Seawolf submarine. And what happened with that was down in Groton Quonset area. There was just a person who was a day laborer, and he was responsible for grinding the sample. And what he noticed was, as he was grinding the sample, the swarf, which is the metal grindings as you grind, were aligning themselves in little 1/16 or 1/8 inch lengths. All right, they ultimately made the decision. I think the submarine hull was already 30% built at the time, something of that sort. They actually tore it down, because for a submarine, those little 1/8 inch flaws that align, if they're down at their full depth charge, or if they're actually operating under the buoyant pressure of the ocean, those cracks can align themselves over time, and it will cause catastrophic failure of the submarine. So the other issue is, for certain industries, for aerospace industry, you have to demagnetize the sample after you've done the inspection. If you don't demagnetize the sample, you can actually get other issues related to interference with the controls and circuitry. So that's something to take into account. History of magnetic particle testing. So 1868, there was individual Saxby, and what happened was he had a magnetic compass, and he was actually working on cannons. And it's almost the same thing I just described for the submarine. The swarf and the grindings were aligning themselves on the cannon from the machining process. Following up on that, there was the principle of magnetic leakage fields. So one of the things, I'll pass these around. If you look at these tagged pages on these various handbooks, so these are handbooks that people who want to go get certified as a field inspector, this is like their training handbooks. What you can do is, there's just simple figures. It's not even, most of the time the people doing these maybe have high school degree or community college degree, associate's degree, but they try to keep the training very simple. So what I want to show you here is these techniques are not rocket science. It's not, high level computing, things like that, very basic, but a lot of it is what ties into what's known as common sense engineering, because they've learned from failure over the years by not doing the techniques properly. So if you look, this is for penetrant testing, this is for magnetic particle, and this one shows the hysteresis curves and what is known as your flux leakage fields, depending on how you apply the yoke to the sample. In 1917, a lot of times what we will see is war. When countries go to war, that is the impetus for development of the technology. So there's an individual working for American Bureau of Standards, and same type of thing. They just noticed these things while they were, it's not like Rosie the Riveter, they're doing the same thing over and over. And as he was grinding, he's saying, well, why are the grindings aligning themselves? So it was as simple as that, how magnetic particle testing came about. During First and Second World Wars, the technique was further developed for specific applications, whether it was naval applications, aviation applications, or other. Important to know when we're dealing with magnetization is, yesterday I'd put Maxwell's equations on the board and we talked about E&M principles and processes, Faraday's law, Ohm's law, things like that. When you have a sample that's being magnetized, you need to recognize that the orientation of the flaw with respect to the magnetic field is a very important variable. So if you have a flaw and it's not aligned perpendicular to the magnetic field, it can be a missed indication. So that's why oftentimes in the field, they will do the magnetic particle testing at like a 0, a 90, and a 180. Just because and sometimes they'll do it at plus or minus 45s to just ensure that the orientation of the field is not a reason why they're missing indications in the sample. The choice of the powder, you can actually choose different magnetic powders, and then whether you use a direct current or alternating current with respect to electric fields and magnetic fields, that also makes a difference with the industry that is being, whether it's aviation, naval, or bridges and construction infrastructure. In terms of the sizing, again, this needs just take into account that oftentimes this is related to they call them engineering flaws rather than flaws from service use. But 6.3 to 0.25 millimeters is reported as detectable. There's a lot of variables that go into play. So as you see, you can see just based on this number alone, it is over order of magnitude range that they report they can detect. So if they report they can detect over order of magnitude, they can also miss an indication over that same order of magnitude. Limitations of the technique. So if you are LNG tanker, so liquefied natural gas, a lot of times they will use some type of fireproofing, and it's or a paint coating over the base metal. So the paint coatings over the base metal can adversely affect the sensitivity of the inspection, depending on how thick the coating is. As I said before, the orientation of the flaw. The other thing is if you're using electroplating or nickel plating, so for chrome bumpers, things like that, if it's a plating technique, there can be interference for the magnetic fields. You have to, after the inspection, you need to remove those fine iron powders. If you allow those powders to get ingested into an airplane engine, it can actually cause abrasion of the thermal barrier coating. So you're attempting to prevent failure by doing non-destructive testing, but you can inadvertently cause foreign object damage, or you can swing the pendulum to cause a different type of failure mode if you don't clean the sample properly. And there's various types of magnetic ways you can magnetize. You can use ring magnetization, bar magnetization, or yoke magnetization. So this is an image here. This is, when I say a yoke, this is what the yoke is. So if there was somebody out in the field, you're limited by how far the yoke can go, right? So the magnetic field only applies in between the areas where the yoke are. So they're actually only looking for flaws right at that edge. And if you look, you can see the fluorescent right there. That's where they're looking for the flaws. Versus if you have a cylindrical tube, you can use a bar magnetization around it, similar to a heat exchanger coil or things like that. I had discussed yesterday friction stir welding with the eddy current lecture. So there's a lot of similarities between the trade-offs. So things that are good for eddy current testing are usually seen as not good for magnetic testing, and vice versa. So what you're seeing here is actually friction stir welding this is the anvil, and this is the rotation of the anvil over that it's butt welded section. This is the friction stir weld right here. You have the root of the crown of the weld and the root of the weld at the base here. And what you're actually seeing is, as you scan over it, you can see the heat affected zones. This is known as the nugget of the weld. So the nugget is the central area here. You can see the heat affected zone, which is a product of the frictional heat as it joins those two sections together. And then other issues you're seeing here is you also see that it's not a non-uniform heat affected zone, and you're seeing a little bit of striping effects, but the striping effect is away in the base metal. So the base metal's further out, then you have a heat affected zone, then you have the weld nugget. Last thing I wanted to discuss is just to bring a piece of equipment in. This is not related to magnetic particle testing, but this is related to thermography. So if you have seen nuclear power plants, these large concrete cooling towers, or if you see a bridge decking component, which has a thick concrete or asphalt layer over the decking, one of the techniques they'll use is just based on thermography. So this is actually where the technologies advance with respect to the ability to use computing. And this used to be a system that would probably be the size of this table, and it was not portable. And in about 20 years, they've been able to miniaturize the equipment so that it's handheld, and you can actually walk along a structure. And you can actually, using the thermography, you can see if there's leaks. And it's another industry where they use this is called, if a building wants to get LEED certified for, you see, if you're going to walk towards Hayden Library, there's a plaque and it says LEED Gold. LEED is related to, they designed the building so it's environmentally friendly. This is actually an entire industry built around this. It's called commissioning. And what happens is if they'll go into a building or something, they'll go around windows, or they'll go around, if you're looking on high rises in downtown Boston, they'll look for leakage where the environmental, whether it's cold air or something like that, is infiltrating past the curtain wall, past the glass facade. Or they can also use it for concrete structures if there's an area in the containment tank that is hotter than the other. Oftentimes there could be voids in that concrete, subsurface voids, depending on how deep the concrete is. So I wanted to show you Just the various, simple as basically you have some lenses, and then this just works on temperature gradients. So it's as simple as that. For the people on the video, if you have any suggestions for what you want to discuss on the final lecture, I want you to email me, because I'm going to basically take suggestions on what we discuss. We can talk about coordinate measuring machines and point clouds and how they can import point clouds into SolidWorks models and reverse engineering. We can talk about preventative maintenance over time, but I want to leave it up to you to let me know if there's specific topics you want to be discussed in the lecture next week. So does anyone have any other questions related to either penetrant testing, magnetic particle testing, thermography, or anything we've previously discussed?
How do you demagnetize something?
So in that handbook, the question was, how do you demagnetize something after you've performed the inspection? So in that mag particle handbook, it's related to the hysteresis curve of the magnetization curve. So you know how much you've magnetized it, and basically you can just tune it in the opposite direction. It's as simple as that to remove it. But then you also do a check afterwards, so you can put a bar magnet or something, just to make sure that it's still fully demagnetized. It's pretty simple. All right, so that's all I wanted to discuss today, and I'll see you guys next week.